Okay, welcome back. Now the demo that I'm going to do is a really good demo. It's called Physical Pendulums and Moments of Inertia. So I'm going to show you different kinds of physical pendulums, and I'm going to show you how the period of the oscillations is intrinsically connected to the moment of inertia of the object about the pivot point. So the first one I'll start with is a ruler. I'll pivot it about the end, and I will displace it from equilibrium, and I will ask, if I displace from equilibrium and let it go, what is the period of the oscillation, right? So the equation is the period is equal to 2 pi square root of I moment of inertia about the pivot point over mgd. So let me explain what this means. If the ruler is pivoted about the end, it will be the moment of inertia of a ruler about the end. Right, and then the mgd will be, if I displace this from equilibrium, right, wherever the weight is concentrated, the weight is concentrated at the center of mass, this is mg, and then the distance d is the distance from the center of mass to the pivot point, and that's what is causing torque. The mgd is basically, essentially the torque on the system that's causing it to go back and forth. So the greater the torque on the system, the shorter the time that it will take, right? But the bigger the moment of inertia, that's going to cause it to take a longer time, right? The moment of inertia is how sluggish the system is with respect to the pivot point. So if we do the end of the rod, right, the period is expected to be what? The moment of inertia of a rod or ruler about the end is 1/3 ml squared. 1/3 ml squared divided by mgd, right? And then the distance d will be half the length of the rod, right? So then it's going to be L over 2. And then the mass of the ruler is going to cancel. So it's going to come out 2 pi 1/3 times 1 squared, since it is a 1 meter stick, right? And then you have here 9.8 times 1 over 2, right? So then the 2 goes up to the top, and we get 2 pi square root of 2, and then the 3 multiplies by the 9.8. 9.8 times 3. Right? Okay, so let's measure that. Let's see what it comes out. I'll put the stopwatch right here. Okay, displace it from equilibrium times 20 cycles. Ready, set, go. 1, 2, 3, 4, 5, 6, 18, 19, 20. 20 seconds took 32.86. Right? So pretty close to this. 1.639 seconds, 1.643 seconds. Tad bit bigger. I mean, the error is so insignificant that it's just simply due to my reaction time to stop the stopwatch, right? So pretty much almost zero error, you can say. 1.639 to 1.643, right? So it really matched. Now, what if I make the pivot point something different? Okay, let's say I make it the 66 centimeter mark. Then I displace it, and it goes back and forth, right? So let's see, what should that be? Okay. So what changes? Now the moment of inertia changes quite a bit, right? The pivot point is going to be the 66 centimeter mark. Right? This is 66 centimeters. And then the center of mass is right here. Right? So the distance d is going to be the distance between the 66 and the 50 centimeter mark, right? This is the 50 centimeter mark. So this is the distance d is going to be 0.16 meters, right? So let's see, the mass still cancels. So let's start from the beginning. What is the moment of inertia about that pivot point, right? Well, then you use the parallel axis theorem, right? 1/12 ml squared plus md squared, right? So you use the parallel axis theorem, shift the center moment of inertia to that point. Then you divide by mgd. This d and this d are the same. In other words, the amount that you're shifting from here to here, right, which is equal to the distance from the center of mass to the pivot point, that's the shift amount. It's increasing the moment of inertia, right? But it's also increasing the torque, right? So it's increasing the torque on the system. So that D appears twice in the system. So this mass and this mass cancels and this mass cancels. So then we have period is 2 pi square root of, then you're going to do 1/12, 1 squared plus D is going to be 0.16 squared. Okay, divided by 9.8 times 0.16. Okay, so let's see what we get here. The previous one was 1.639 seconds, so this is expected to take a little bit longer, right? It's expected to take a little longer. Why? Well, because even though the moment of inertia is less than being at the end, right? The end moment of inertia is the most. So in other words, by making the pivot point the 66 centimeter mark, we actually went down in the moment of inertia. So it became easier to rotate. But we also went down in the torque. The torque went down too, right? So the torque went down more than the moment of inertia going down, and therefore, if this went down, since this went down more than the moment of inertia going down, that means the period overall increased. That means it's slower overall, right? So this is 1.63656 is greater than the 1.638 seconds, which was the expected period for the other one, right? Okay, so now let's actually run the experiment. Let's count 20 cycles. Ready, set. 1, 2, 3, 20. 33.23 seconds, right? So at the end, it was, the friction slowed it down so much that it was almost stopping. So the T experimental was 33.23 seconds. Then you divide that by 20. It did take more time than when it was at the end. 1.662, slightly larger than the expected, but definitely much larger than when it was at the end, right? So 1.662 is larger, and then our error is very, very small also, okay? Now, what if we have something like this? Okay, displace this and let it go. This one probably can't last 20 because the friction is going to slow it down. I can do like 5 cycles, measure 5 cycles. So what is the expected for that one? Okay, we're going to have to measure the radius. Okay, that comes out to be 7.52 centimeters. The other thing that we have to measure is the distance from the pivot point to the center of mass, right? From the center of the disc to the center of the hole. That's my D, my shift amount. So that one comes out to be 4.32 centimeters. 4.32 centimeters. So what would be the equation now? Now I'm going to do the moment of inertia of a solid cylinder about the center of mass. Then I have to shift it, right? So the moment of inertia of a solid cylinder is going to be 1/2 mr squared, then shifted md squared, over mgd. Again, the mass cancels. Okay, so these two d's are the same again. So now you see the routine, right? They are always the same. So then the expected period is going to be 2 pi square root of half of the radius squared. So 0.0752 squared plus the shift amount squared, 0.0432 squared, divided by 9.8 times 0.0432. Okay, 62 seconds is the expected period of oscillation. Now let's count 5 cycles. Okay, go like that. Ready, set, go. Ready, set, go. 1, 2, 3, 4, 5. So you can see that it's slightly larger than that because maybe there's some reaction time involved. If I time it again, let's see if I get a better result. Ready, set, go. 1, 2, 3, 4, 5. 3.33 seconds now I get. Okay, so 3.33. Then if I divide that 0.666. Okay, that's pretty close, right? 0.666, 0.662. So very, very close to the result that I would expect. So all of these theories about moments of inertia, shifts, torques, they are all working out to be true, right? One other one we could try, quick one. This is a great lab that you can do and a great demonstration of moments of inertia and period of oscillation. Okay, now go like that. This one we could probably measure 20 cycles. Let's do the experimental first. Ready, set. 1, 2, 3, 4, 5, 20. 20 took 19.93 seconds. 997 seconds is the period, right? So now what's the theoretical? Well, now I need to measure the inner radius, the outer radius, right? Diameter is going to be roughly about 20 centimeters, right? 20 centimeters is the inner diameter, and then 27.4 centimeters is the outer diameter, 27.4. 7.4, okay? And then the distance from the inner circle to where the hole is, that distance is going to be from the inner radius. Inner radius 1 is going to be 10 centimeters, right? Which is going to be half of the diameter, right? So that's 0.10 meters. The outer radius is going to be half of 27.4, so that's going to be 13.7 centimeters. So 0.137 meters. Right, and then the distance from the center of the ring all the way to the hole, that's the distance d of the shift, right? That's going to be 0.10 meters plus the 1.9 centimeters extra, right? That's the extra from the inner radius all the way to the center of the hole. So that's going to be, change that to meters, it's going to be 0.019 meters. So this is going to be 0.119 meters. That's the shift amount. Okay, so then what's the moment of inertia? 2 pi. The moment of inertia of a ring is 1/2 m r1 squared plus r2 squared plus the shift md squared over mgd. So you see it's always the same pattern. The m's cancel, and then this one you square the inner radius, you square the outer radius, you add them, you divide by 2, and then on top of that you add the distance, the shift amount squared. Okay? So then you're going to have your period theoretical, 2 pi square root of 1/2. The inner radius was 0.10 squared, plus the outer radius was 0.137 squared, plus the distance of the shift amount is 0.119. And then square that, divide by 9.8.119. Okay? So 0.5 seconds. So you see the theoretical period is almost 1 second. 0.983, and I got 0.997 seconds. So again, I could measure the period again 2-3 times, repeat it, take the average value, compare that with that, and then get a % error. So you can see the result is very, very good. It's going to be probably less than 1% error, right? So then I can now do any other kind of shape too. Okay, so I could do some other shapes like this. Okay, I could put it from this corner, measure the period of oscillation. This is basically half of an ellipse. It's this distance is larger than this distance. So you're taking half of an ellipse, and you can either rotate it about the top or rotate it about here. Or you can get a triangle, right? Any kind of triangle, or you can get any other kinds of shapes, right? And rotate it. So let's say I rotate it from this top right here. Okay. Go like this. And then let's measure the time. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 cycles is taking 21.16 seconds. Okay, so now let me measure the dimensions of this along the bottom base. The size, the base is about 40 centimeters, right? So I have here 40 centimeters like this. Okay, and then the height of it from the top to the bottom, that's going to be 34 centimeters. Okay, 34 centimeters from here to here. So the hole that I had it pivoted about was the hole at the top. Okay, so I'm going to assume that the hole is pretty much way at the top, not necessarily, in reality it was a little bit below, but the calculations are going to be pretty complicated if we do the actual hole, but the results aren't going to be too much different if I assume that the hole is way at the top vertex, right? So let's assume the hole is way at the top vertex. How would I find the moment of inertia of that shape? So let me draw this way. Like this. This hole I'm going to draw as if it's at the origin. Okay? So like this. This base, the height here, which is 34, I'm going to put this way. This is 34. Right? And then from here to here is going to be 20 centimeters. Right? Then it's going to look like this. So it's like asking the question, what is the moment of inertia? If this is the x-axis, this is the y-axis. What's the moment of inertia about the z-axis? The z-axis is coming out, right? Going through the corner edge, right? The z-axis is coming out. So what's the moment of inertia of that shape around the z-axis, right? So the shape that's at this half is going to be at the bottom. So if I find the moment of inertia of the top, I can just pretty much double that, right? If I double that, that gives me the total moment of inertia because this is symmetric, okay? So how do I find the moment of inertia of something like this about the z-axis? The way to do that is by doing a double integral and taking dx dy, finding the moment of inertia of that, right? So how is that going to be? So the moment of inertia about the z-axis, right? Integral r squared dm. Okay, so then what's my r squared? The r squared is the distance from here to here, right? This is r, so that's going to be x squared plus y squared, right? X squared plus y squared. And then dm is going to be the surface mass density, right? Sigma times dA, and then dA is going to be the area of that, so it's just dx dy, right? Dx dy. And then you do a double integral here, right? And then the sigma, which is the surface mass density, comes out. I z-axis, right? Then you have integral like this. So what are the limits of that integral? X squared plus y squared dx dy. Okay, so what are the limits of that integral and which one should we integrate? Well, you can integrate in terms of x or in terms of y if you want first, but what I'm going to do is I'm going to integrate in terms of y first. This one, it represents a straight line. Y equals mx plus b, so we can come up with an equation for that straight line, right? Y equals mx plus b, so the y-intercept is 0, right? So since it starts at the origin, the slope is going to be the rise over the run, so y is equal to 0.2 over 0.34 x, right? Teen x. So that's my y equation. So I'm going to integrate this in terms of y first. Remember, sigma we pulled out is the surface mass density. Go from 0 to 10 over 17x, right? Because y goes from 0 to 10/17 x, and then x goes from 0 to 0.34, right? X goes from 0 to 0.34. So I integrate in terms of y first, and then in terms of x, okay? So then this is going to be what? I equals sigma integral 0 to 0.34, right? And let's remove this rod. Okay. So then we have here integral of x squared in terms of y. It's just going to be x squared y plus, then your integral of y squared is going to be y to the third over 3. Then you integrate this from 0 to 10/17 x, right? And then the dx is here. So then for y, we put in 10/17 x, And for this y, we put 1017x, and then we put in 0, we just get 0, right? So I is equal to sigma x squared, okay, 0 to 0.34, and then we put in 10/17 x, right, plus 1/3 10/17 x cubed. Okay, then we are going to integrate that in terms of x, right? So it's a good application of double integration. Okay, the moment of inertia, sigma, so we just combine this 10/17 plus 1,000 over 3 times 17 cubed, right? And I can just factor that out of the integral because it's just a constant. So then I have integral of x cubed dx from 0 to 0.34, right? So then the integral of that is pretty simple. I just end up getting x to the 4th over 4. The 4th over 4, right? Because the 0 is just going to give you 0. So then I put down what the surface mass density is. That's equal to the mass divided by the surface area. So what is the surface area of this? Half base times height, right? Half base times height. So I take all of these numbers, I divide by half base times height. So this is just going to give me the base, the 2 is going to cancel this. It's just going to give me 0.1, right? So then the moment of inertia of just half of the object, right? That's going to be 10 mass m of the object. But this is the moment of inertia of only half of that object, right? So then because the object look like this, I'm going to have to double that, right? So the moment of inertia is going to be this times 2. So you multiply that by 2, right? So that's going to be the moment of inertia of the whole object, both of the sides with respect to the top vertex point, right? So then I can start applying the period equation. Okay? So then we displace this from equilibrium, right? And then it went back and forth every 1.058 seconds. So then we need to know where the center of mass of the object is, right? For this one, we're going to, instead of doing it calculationally, we're going to calculate the center of mass experimentally. They hung the object from 3 different points, right? And then they drew a line, and then hang it from this point, draw a line, and then hang it from another point, draw a line. If you hang it from 3 random arbitrary points and draw lines, they should always go through the center of mass. So the center of mass of the object is here. So when I measure the distance from the center of mass as given by those 3 lines, that comes out to be 23 centimeters. Yeah, the 23 centimeters from the center of the hole, 23 centimeters all the way up to the vertex. Moment of inertia, I already calculated the moment of inertia about the pivot point, so I don't need to do any shifting. So I can just put down 0.12893 m, divide that by m 9.8, and then 0.23. Okay? So that's, okay? So my experimental answer was 1.058 seconds. So the theoretical is a little bit larger. So some of the sources of error were that the dimensions that I measured, they weren't exactly 40 centimeters. The 40 centimeters, it was like 39.5, but I rounded it up to 40, right? This dimension here was not exactly 34, but I rounded that also to 34. Also, the pivot point was not exactly at the top point, but it was a little bit off the top point. So all of those can affect the results and can cause a little bit of error due to the uncertainty of the base, the height, and also the pivot point, right? So in this video, you've seen lots of good stuff without moment of inertia, shifting, doing double integration, and then measuring the period of motion of different physical pendulums, okay? Thank you very much.